myself Anamika Goyal, Assistant Professor in the Department of Computer Science and Engineering (AIML) from ABES Engineering College, Ghaziabad. Today we'll be discussing about the topic asymptotic notation in the subject of design analysis of algorithm. In today's lecture, we'll be covering following topic. First, the introductions of asymptotic notations, then Vigo notations, after that omega notation, and finally we'll discuss about theta notation. So let's start our first topic, asymptotic notations. Asymptotic notation is a mathematical way of representing time complexity of an algorithm. Now, what is time complexity? So the amount of time that an algorithm to take for its executions is called time complexity. By using asymptotic notations, we are able to measure the complexity of any kind of algorithm. Here we have three asymptotic notations. First one is Vigo notations, then omega notations, and theta notation. Let's discuss each one in detail. First, we'll discuss about Vigo notation. It is most frequently used notations used to measure the time complexity of an algorithm. It is also known as upper bound of an algorithm. Vigo notation basically used to represent the worst case time complexity of an algorithm. Here, what is the meaning of worst case complexity? The worst case means the maximum time of an algorithm is taken is called worst case. Suppose I have an array of 10 elements and I want to search a particular element into the available list of elements, and the element which I want to search may be not present in the list, or if it is present, so it will be the last array of index. So that is the case of worst case analysis. So to understand the concept of Vigo notation, let's see the graph. In this graph, x-axis represent the value of n, that is what? Number of input variable of an algorithm, and y-axis represent time. Here we have two functions. One function is f of n and another function is g of n. Now we are representing functions of n in terms of gn. The representations of function n in terms of gn will change from notation to notation. So according to Vigo notations, functions of n is equals to order of gn if there exists positive constant c and n naught such that f of n is less than equals to c dot gn for all n where n is greater than equals to n naught and c is greater than 0. Let us see the graph. Here what is n naught? N naught basically the intersections point between functions of n and gn. Here you can see after the n naught, the value of functions of n is always less than or equals to function of gn. So we can say that gn is nothing, it is an upper bound of functions of n. To understand it, let us see an example. Here we have a functions of n is equals to 4n plus 1. Now I have to calculate the time complexity of function n using Vigo notations. So as per the conditions of Vigo notation, here function of n is less than equals to c dot gn, where c is nothing, it is a positive constant. Here the value of function n is equals to 4n plus 1. Now what about gn? Let us assume the value of gn is equals to n. Why we choose n here? Because the value of function of Gn is depend on the value of function of n. The value of higher degree coefficient of function n will consider as a Gn. For example, if the value of function n is equals to 4n square plus n, so the higher coefficient is n square. So here we consider the g of n is equals to n square, just like that. Is it clear? So 4n plus 1 is less than equals to c dot n. That is what? That is the equation number 1. I hope you understand. Now, to satisfy equation 1, here we put the value of c. If the value of c is equals to 1, put in equation number 1. So what happened? 4n plus 1 is less than equals to 1 dot n means n. Is it true or false? No. Is it false? 4n plus 1 is less than equals to n. This is false. Now we put the value of c is equals to 2. In that case, 4n plus 1 is less than equals to twice of n. This condition is also false. Again, we put the value of c is equals to 3. In that case, 4n plus 1 is less than equals to thrice of n. Again, not satisfied. Now put the value of c is equals to 4. In that case, the value of 4n plus 1 is less than equals to 4n. Again, not satisfied. Now put the value of c is equals to 5 in equation 1. So the value is 4n plus 1 is less than equals to what? 5n. Now the condition is satisfied. Is it clear? Again, we'll check the value of c is equals to 6. In what is the value of c is equals to 6? In that case, equation 1, 4n plus 1 is less than equals to 6n. Conditions again 2. For c is equals to 7 is again 2. So, in the case of Big-O notations, we always consider the least upper bound value of c. So, here the least upper bound is c is equals to 5. Okay. So, here we put the value of c is equals to 5. So, 4n plus 1 is less than equals to 5 of n. After finding the value of positive constant c, we'll find the value of n naught. What is n naught? It is the intersection point between function of n and g of n. So, for n naught, in equation number 2, we put the value of n is equals to 1. Why we put 1? Because we always assume at least minimum 1 unit of time each instructions will occupy as a time complexity. So, n is equals to 1 unit. Here, 4n plus 1 means 4 into 1 plus 1. It means 4 plus 1 is equals to, 4 plus 1 is less than equals to 5 into n means 5. Here, 5 is equals to 5. Condition is satisfied. 4 plus 1 is 5. 5 is equals to 5. Condition is satisfied. Again, we'll check n is equals to 2. So, what happened? 4 into 2 is 8. 8 plus 1 is less than equals to 5 into 2, 10. 9 is less than equals to 10. Condition is again satisfied. So what is the value of n is here? N is always greater than equals to 1. In that case, equation number 2 is always satisfied. So we can say that the complexity of functions of n in terms of Gn is function of n is equals to functions of n is equals to order of n for all the value of c is equals to 5 and n is greater than equals to 1. That is what? That is Big-O notation. I hope you understand very well. Our next topic is omega notations. Now, omega notation, it is also known as lower bound of an algorithm. Omega notation is basically used to represent the best case time complexity of an algorithm. Here, what is the meaning of best case? The meaning of best case is the minimum time of an algorithm is taken out. For example, in case of linear search, if I have 10 number of array, I have 10 number of element in an array, and the element which I want to find in a list of element is available at first location of an element. So here the time complexity is order of 1 unit. So that is the best case time complexity. So to understand the concept of omega notations, let us see the graph. Again in this graph we have two functions. First one is f of n and second one is g of n. Right? We are again represent the function of n in terms of gn with the help of omega notations. The functions f of n is equals to omega of gn if there exists positive constant c and n naught such that f of n is greater than equals to c dot gn for all n, where n is greater than n naught and c is greater than 0. In this graph, you can see what is n naught, that is the intersection point between function of n and functions of gn. You can see that after the intersections point n naught, functions of n, the value of function of n is always greater than equals to g of n. So here we can say that function of g of n, it is the lower bound of a functions of n. So to understand the concept of omega notation, let us see an example. Here we have functions f of n is equals to 4n plus 1, and now I want to calculate the time complexity using omega notation, right? So again similar problem, I have one function f of n is equals to 4n plus 1 and we assume the functions of gn. Now what is the value of gn? The highest coefficient of functions of n, that is n, 4n. Here we ignore the coefficient and constant values, so the g of n is equals to n. So put the value of function n and g of n in the equations of omega notations. So the equations of omega notations is functions of n is always greater than equals to functions of gn. Here put the value of f of n is 4n plus 1 is greater than equals to c dot n. That is what? That is the equation number 1. Now, to find the value of a positive constant c, here we put the value of c is equals to 1, equation number 1. So, what happened? 4n plus 1 is greater than equals to 1 dot n. Is it true or false? Is it true? Condition is true. Again, we'll check c is equals to 2. So, 4n plus 1 is greater than equals to 2 of n. Condition again true. For c, similarly, for c is equals to 3, 4n plus 1 is greater than equals to 3n. Condition true. For c is equals to 4, 4n plus 1 is greater than equals to 4 of n. Conditions again true. Now what happened? Again we check for the value of 5. If I put the value of c is equals to 5 in equation 1, so what happened? 4n plus 1 is greater than equals to 5n. Is it true or false? No, it is false. So what is the value of c? In case of omega notations, we always consider the greatest lower bound. The value of greatest lower bound is 4. So the value of c is 4. C is equals to 4. After that, the equation for c is equals to 5, the equation is not satisfied. So we put the value of c in equation 1. So 4n plus 1. 4n plus 1 is greater than equals to 4n. That is what? That is the equation number 2. After that, we find the value of and naught. What is and naught? The intersection point between function of n and gn. So in equation number 2, we put the value of n is equals to 1. If I put the value of n is equals to 1 in equation 2, that is 4 into 1, 4 plus 1, that is 5. 5 is greater than equals to 4. Yes, condition is true. For n is equals to 2, 4 into 2, 8 plus 1, that is 9 is greater than is equals to 4n. 4n plus 1 means 4 into 2, 4 to 8 plus 1, 9. 4 into 2, 8. 4 into 2, 8. So 9 is greater than equals to 8. Yes, condition is again true. So we can say the value of n is always greater than equals to 1 for satisfying the equation number 2. So here the complexity of functions of n is equals to omega of gn for c is equals to 4 and n is greater than equals to 1. That is what? That is omega notation. I hope you understand the concept of omega notations. Our last notation is theta notation. Theta notation, it is also known as type bound of an algorithm, or we can say it is the combinations of upper and lower bound of the algorithm. It is basically used to represent the average case complexity of an algorithm. What is the meaning of average case? In case of average, suppose let us take an example again, linear search. If I have an array of 10 elements and I want to find a particular data item into the available list. So if an array contains 10 elements and I want to searching a particular list of items which is available at the mid of that array, it means position number 5. So what is it? That is called average case complexity of an algorithm. So to understand the concept of theta notations, again we see the graph. In this graph, x-axis represent the number of input variables and y-axis represent the time. So here we have a functions f of n. This is what? This is the functions of n. And another function g of n with positive constant c1. So that is what this represents c1 of gn. You can see that functions of n is always greater than or equals to c1 g dot n. So here c1 g dot n represent what? It's represent lower bound of an algorithm, right? Lower bound of that algorithm, that is called omega notations. We also have another function, that is what? That is C1 of Gn and C2 of Gn. According to that, you can see the functions of n is always less than equals to C2 dot Gn. So what is it? So C2 dot Gn will represent upper bound of an algorithm. What is it? That is big O notation. That is what? That is big O notation. So what is it? Basically, theta notation, it is the combinations of omega notations and big O notations. Here you can see we have two intersections point. Two intersection point. First one is this. This is what? This is n0 dash. And another intersection point is n0. Right? So, which intersection point will consider the highest coefficient value will consider it. In that case, this is n0 net and this is n0. So, we consider n0. Okay? Consider n0. Okay? So, as per theta notation, the functions f of n is equals to theta of gn if there exists positive constant c1, c2 and not such that c1 gn is less than equals to f of n is less than equals to c2 dot gn for all n1, n2 is greater than n0 and c1, c2 is greater than 0. To understand the concept of theta notation, again let us see an example, similar example in previous slide. F of n is equals to 4n plus 1 and I want to calculate the time complexity using theta notation. As per the given conditions of theta notations, that is what? That is theta notations. So C1 dot Gn is less than equals to functions of n is less than equals to C2 dot Gn. That is what? That is omega notations. No, it's not omega, it's theta notation. What is it? It is theta notation. So here we put the value of f of n in Gn. In that case, the value of f of n is equals to 4n plus 1. And again, the value of g of n is the higher coefficient value of function of n, that is n. So C2 dot n. Now, if you see the equation number 1, so here, second half portion of that equation, like 4n plus 1 is less than equals to C2 dot n. This is what? This is the upper bound of an algorithm. It means it is big O notations. We already solved this example. In case of big O notation, here the value of C2 is equals to 5 and the value of n is equals to what is greater than equals to 1. That is what? That is big O. Is it clear? We already solved it. And in this equation number 1, the first half portion, that is C1 dot n, is less than equals to 4n plus 1 is what? It represents omega notation. It represents omega notation, right? We already solved it. In that case, the value of C1 is equals to 4 and n is greater than equals to 1. So what is theta notation? It is the combinations of omega notations plus big O notation. Is it clear? So in this equation, we can say that as a theta notations, functions of n is equals to theta of n for C1 equals to 4 and C2 equals to 5 and n is always greater than equals to 1. That is what? That is the theta notations. So, I hope you understand these all kind of notation for the calculations of time complexity. These all are the references which I use in my presentations. This is all about in my side. Thank you for watching my video.